extraction.
Well, thank you very much, and thank you all for being here. It's a pleasure to follow Carlos. It's a fascinating presentation and such great work. So I want to talk about just a few of the potential environmental impacts. I'm going to provide one water example and one air example covering the space today, but we don't have too long, so I'm going to forge ahead. I'd like to acknowledge my colleague Avner Vengosh at Duke, who has done a lot of the water work together, and I'll acknowledge some other people as we go along too. So the first thing I want to talk about are some potential water interactions, and I think most of these, perhaps all of these, will be familiar to you. These are just a few of the ways in which an oil and gas well, a hydraulic fracturing operation, really an industrial activity, could interact with water sources across the landscape. There's a stream here, could be a pond, a lake, there's a water or a wastewater pit here. There are chemicals and surface activities here. My first job is with the Dow Chemical Company, and so safety in terms of handling of chemicals is obviously extremely important. And then the area that I'll focus on today is down here, really thinking about the shallow part of the well integrity, if you will, the first couple of 100 meters, rather than what most people, at least in the public, worry about, which is what's going on a mile or two underground. And our data suggests that it's this shallower area, this issue of well integrity, that is the biggest issue in causing the minority of issues, minority of things that arise. So one of the take-home messages for the talk today is that best practices and policies matter and make a positive difference. This is work originally by Stephen Osborne, a postdoc in our group. This is a later iteration of a figure that what we did here was to ask a simple question. That question was, is a person's drinking water any different if they're living near an oil and gas well than if they're living farther away from an oil and gas well? So each of the dots on this figure is a private water source, a well from an individual home. What you have on the x-axis is the distance to the gas well. The y-axis is the methane concentration that we observed in the well water. And the band is the level of action, or the action band set by the Department of Interior. So they recommend considering action down here at 10 milligrams per liter, and once you're up here about 28, the methane is saturated, if you will. So these ones up here are above saturation. They'll bubble when the water comes up out of the ground. So what you see here are a couple things. First of all, there's naturally occurring thermogenic methane in most of the water in this area. It has nothing to do with oil and gas extraction. It's just a legacy of being over source rocks in this region, the migration of those hydrocarbons over thousands and millions of years. But you do see a relationship, at least for a minority of houses, down here within a kilometer or so of wells. We see higher methane concentrations near them. And that's especially true when we look at ethane instead of methane. Now, ethane has no natural biological sources in this environment. So here the curve is essentially flat. And then we see about a dozen or so points here where the ethane are quite elevated. And the only times we see propane in detectable levels in these water samples are within about a kilometer. So, this is suggestive that there's the potential for an interaction between 1 kilometer or so, and lots of things discuss about these data. We do not have pre-drill data, so what you'd want in each case, of course, is a pre and a post sample. But anyway, so that's the first thing to look at. So let's hone in on the Marcellus. That's where we were a minute ago. Let's stick with the Marcellus. Now you're looking at just a simple relationship between salinity, in this case chloride, and the methane, in this case normalized to argon-36. So here what we have is a basic relationship that also is not surprising. There's a broad range of naturally occurring methane in this system, and when you find high levels of naturally occurring methane, you almost always find saltier water. So there's a log plot here and a log plot here. And the interesting thing about this plot is that it doesn't make any difference whether you're within a kilometer or farther than a kilometer away from an oil and gas well. You have the same basic relationship. And that's what you'd predict, because the well pads are not being sited, they're not being placed because there's a high surface methane concentration. They're being placed to cover the landscape of that shale that's a mile or two underground. So you don't expect a relationship in this case. And statistically, there isn't one based on this Chow test. But then once in a while, there are these unusual samples. And these are the cases in particular where you have very low salinity water and very pure water, and then all of a sudden, the methane concentrations are saturated or supersaturated. And even since then, now we've now seen in a handful of houses the water quality change through time from here to here. So these are the cases that we think are an interaction with the oil and gas wells, and we think that the first and foremost issue, as I mentioned, is well integrity. So Carlos talked a little bit about sourcing and isotopes and such. This is a plot, again, of distance to a gas well. I should say the previous work was led by Tom Dara, who's now at Ohio State. Distance to gas wells on the x-axis, helium to methane on the y-axis. And so why noble gases? Well, we use noble gases because they don't change. They're not fractionated. They're fractionated by physical processes, but they don't undergo reactions in the same sort of multiple things that can happen to a hydrocarbon like methane. So they're a stable tracer, if you will. Here you're looking at the range in helium to methane across this 10-kilometer distance to gas wells. You've got a naturally occurring salt spring here. All right. Then you have source gases here that are shallower, upper Devonian gases, and then the source gas itself from the Marcellus down here. Within a kilometer, you see a full range of data. So you see homes that are perfectly natural. You see some that appear to match the shallower Devonian, upper Devonian gas, and then you see a handful that appear to match the Marcellus gas as well. All right, why is that? Well, we think, first and foremost, and based on the noble gas data, most of which I haven't shown you here today, that mechanisms 4 and 5 up here are the cause. So rather than hydraulic fracturing opening cracks through the rock and those materials and gases traveling all the way up, or even intersecting with an abandoned well here that I'll talk about in a minute, we think it's either a cement issue in the case of those upper Devonian gases. So if that cement isn't properly constraining the system, then gas from an intermediate pocket can move into, up, and out the annulus, the donut on the outside, and between the rock wall and the casing. Or if the casing leaks, it should match the Marcellus gas itself, and you have mechanism 5. So it's not this that people are most worried about, it's this, either from here or leaking out the casing, we believe, based on the noble gas data. Here's a recent review just a few months ago that Richard Davies led. This is just a summary of oil and well integrity, if you will. It's apples and oranges, it's onshore, it's offshore, it's old, it's new. Very hard to compare across the multiple systems, but it suggests that at least for sustained pressure, there are issues with anywhere from a couple of percent to a few tens of percents in the worst cases and in the oldest wells. But those values, of course, are not equivalent with actual leakage into the environment. And then finally, in an area like this, it's useful, I think, as an environmental scientist to think about the long-term consequences, the legacy issues. So there was a paper out just a couple of weeks ago led by Mary Kang and the Princeton group where they looked at methane emissions from some legacy wells in the Marcellus. These are photos I took a few weeks ago. And I don't know if I have a video, but yeah, maybe I can do it. Let's see. I'm going to get seasick doing this. Oh, of course.
Oh, okay.
Well.
There's a Horse Run Road that's really bad, and it's the very last flood. Like, you know how they flooded the well? Well, that
So you get the
one
idea.
really.
All right. So for water issues, at least for the drinking water interactions, we believe the first and foremost thing to focus on is the shallower well integrity, and obviously the surface operations themselves, what's happening near the surface. I want to finish very quickly just with an air example. In our group, we've been working both upstream at well paths with leaks. You're looking at an infrared camera image there, and then downstream looking at leaks along city streets. Now, once the natural gas is in the pipeline, there's no difference between conventional and unconventional in this case. It's all the same. This was a paper led by Nathan Phillips at Boston University. This was sort of the first publicly available map of natural gas leaks across the city. So here we put a methane analyzer in the back of the car and drove block by block around that city. So red is the road miles driven, yellow are the leaks. And then here's just the relationship from the paper showing that the number one predictor of leaks across the city is old cast iron piping, some of it more than 100 years old. Right, there were several things that have happened since then, and last of which was that in July, Massachusetts passed a new pipeline, accelerated pipeline replacement bill. So again, one of the take-home messages here is that these sort of partnerships where we can replace old infrastructure are really important in these situations. There's a poster presentation tomorrow by Catherine McCain and Steve Wolfsey's group in Harvard that provides the budget, if you will, the summary of the top-down measurements that we've been taking from some of the buildings in the area and from outside the city. So this is an estimate of the total emissions across this area for the Boston Metroplex. and the proportion of the methane that builds up in the air that comes from natural gas. So I'll point you to her talk in the poster tomorrow. One final example, here's Washington, D.C. This was a paper that came out almost a year ago now. You're looking at the Capitol building here. This is an old neighborhood in back, same story. Old cast iron piping. Here's the city itself. Who's doing a good job? And how do we know? Well, here's one example. These are PHMSA data that I took looking at pipeline replacement for the past decade. All we did here was ask which companies are replacing their old pipeline at what rates. So over here on the left, this is the number of years still to go to replace them completely. So here's Ohio. Ohio's had a great partnership between the distribution companies, the municipalities, and the Public Utility Commission to accelerate that pipeline replacement. And you see here that there's essentially none left in that system. The other bookend is Baltimore, Maryland, that is on track to finish replacing their old cast iron piping in about 2150, which isn't fast enough. And then finally, just to show you again that these policies matter, some of the driving we've been doing this year have been to target cities where we're examining some of these policies, and they make a difference. So we see leak rates or leak densities that are 1/10 what we see in some of these older cities. So the policies really, really do matter. So these are just some final reasons to invest in the infrastructure, to repair these pipelines and such. Consumers pay for the lost and unaccounted for gas in many cities. It creates jobs. There are safety issues, air quality issues with ozone formation in some cities and in some conditions, and then a greenhouse gas and climate change justification. Thank you very much.